Hey everyone, and welcome. Today we are jacking right into the core of industrial automation. We're going to take a deep dive into a real workhorse of the industry, the Siemens Simatic S7 400 CPU 412. So let's get into it.
You ever just stand back and wonder that? You look at a massive factory floor, conveyor belts, robotic arms, packing machines, and it's all moving like a perfectly choreographed dance. How does that even happen 24/7 without a hitch? Well, it's not magic. The secret is a central controller, a digital brain that's coordinating every single move with just incredible precision and rock-solid reliability. And that's exactly the kind of brain we're going to dissect today.
So what is this industrial brain made of? Let's break down what we're actually talking about here.
Okay, so the official term is a programmable logic controller, or PLC. Now, I want you to think of this as a super specialized, extra tough computer. It's not built to browse the internet or play games. Its one and only job is to run a factory floor. It has to survive heat, dust, vibration, you name it, all while reading sensors and making split-second decisions. And pretty much every PLC, including our CPU 412, is built around this same core idea. You've got the CPU, the processor that's actually running the program. Then you have the input-output modules. These are the senses and muscles. They read inputs from things like buttons and sensors, and they send commands out to motors and lights. Memory, of course, holds the instructions, a power supply keeps the lights on, and the communication interfaces, well, that's the nervous system, letting the brain talk to everything else. All right, so let's zoom in now. We're moving from the general concept of a PLC to our star of the show, the Siemens Simatic S7 400 CPU 412. This is where we get into the nitty-gritty of what makes this particular brain tick. So the CPU 412 actually comes in a few different flavors. You can see the main differences right here. It really comes down to two things: work memory, which is kind of like its short-term memory for running programs, and how it communicates. The 412.1 is your entry point. The 412.2 doubles the work memory and adds a second Profibus port. That's a super reliable network for talking to devices all over the factory. Then you have the top-tier 412.2PN, which keeps that bigger memory but swaps that second port for Profinet. Think of that as a modern, high-speed Ethernet connection for the factory floor. And the speed of this thing, it's just wild. We're talking 31.25 nanoseconds. That's how long it takes to process a basic command. I mean, in the time it takes you to blink your eye, this CPU has already made millions of decisions. That kind of speed is absolutely essential for managing complex machinery with total precision. But you know, speed isn't everything. In a factory, reliability is king, and this is where the CPU 412 really proves its worth. It has what's called a diagnostics buffer. Think of it like a flight recorder for the machine. It logs every single fault, which makes finding a problem so much faster. The real-time clock stamps every message with the date and time so there's no more guesswork. And then you have these crucial physical features, like a literal key switch to change modes and password protection, which makes sure that only the right people can make changes and they can do it safely. Okay, so this brain is fast and it's reliable, but just how much can it handle at once? I mean, what's its bandwidth? This is where the sheer scale of modern automation really hits you. A single CPU 412 can manage up to 65,536 digital points. Let that sink in. That's 32,768 inputs, things like sensors and switches, and another 32,768 outputs, things like motors and lights. That is an enormous amount of information and control coming from one central point. It really shows you what these systems are built for. And that leads us to a really, really common question. It's a great one. If this CPU is the brain controlling all those thousands of devices, does it also have to power them all? The answer is a definite no, and this is a key part of the design. The CPU is the brain. It's not the muscle. So here's how it works. You have a big system power supply that feeds the whole rack. The CPU itself just sips a tiny bit of 5-volt DC power, just enough to do its thinking. The real work of powering thousands of devices is handled by those dedicated I/O modules. They take the main power and deliver the industry standard 24 volts DC at just the right low current to each and every sensor and valve. This separation of brain and brawn is what makes the whole system so safe and so modular. So we have the hardware, we understand the power flow, but how do we actually tell this brain what to do? How do you program it? Well, the CPU 412 speaks a few different industrial languages. You've got MPI, which is kind of its native tongue, often used just to plug in a laptop for programming. Then there's Profibus DP, which is the high-speed network that connects it to all the other equipment spread out on the factory floor. And of course, on that PN model, you have Profinet, the modern Ethernet standard for really high-performance communication. And to teach the CPU what you want it to do, engineers use a really powerful software package called Step 7. This is the environment where all the logic, all the sequences, all the control strategies are built before being downloaded to the controller. Now, what's really cool is that inside Step 7, you're not stuck with just one way of programming. You've got options. There's ladder logic, or LAD, which looks just like the electrical drawings that technicians are super familiar with. Or you could use something like a function block diagram, which is more visual. And this flexibility is a huge deal. It means an electrician can troubleshoot a machine in a language they understand, while a software engineer could be fine-tuning a complex algorithm in a different language, all on the very same device.
Okay, let's pull the camera back a bit. With all the technology out there, where does a controller like the CPU 412 really fit into the bigger picture? Because in the world of automation, this is probably the most important rule. There is no single best controller for everything. It is always about picking the right tool for the job you need to do. And here's the perfect way to see that. Our CPU 412 is a classic PLC. It is a master of if this, then that logic. If a sensor sees a box, then start the conveyor. It's perfect for the vast majority of factory tasks. But over on the right, you have something like a PAC, or Programmable Automation Controller. These integrate that same logic with really advanced, high-speed motion control for things like complex robotics. You choose the CPU 412 when your main challenge is managing thousands of I/O points reliably and affordably. You don't need to pay for complex motion control if your job doesn't need it. That's what makes it the right choice so often.
And you don't just have to take my word for it. Siemens themselves nail it with this quote. It's the accessible, affordable entry point into serious mid-range automation. It isn't trying to be the fastest or most complex controller on the planet. It's designed to be a powerful, feasible, and incredibly reliable solution for a huge slice of the industrial world.
Which really leaves us with one final thought, right? We live in an age where everyone's talking about AI and the cloud and these ultra-powerful supercontrollers. But the fact that workhorses like the CPU 412 are still so vital makes you ask a really important question. When is choosing the proven, the reliable, and the rugged actually the smarter choice?
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.